So we began our discussion of derivatives by defining what the derivative of a function f of x is. Though we strayed away for a while and focused more on the computation of derivatives, we're coming back to the definition in this lecture. We saw that the derivative of f of x, denoted f prime of x, is the limit as h approaches 0 of f of x plus h minus f of x over h. And note this is a quotient of differences. We have the difference f of the function evaluated at x plus h and the function evaluated at x in the numerator, and in the denominator we have h, but this is actually the difference x plus h minus x. And we're taking the limit as h approaches 0 of that quotient of differences. More importantly, we noted that the function f prime of x is the instantaneous slope generating function for f of x. So what that means is if we plug in an x value and evaluate f prime of x at that particular x, for that particular x value, our output will be the instantaneous slope of the function f of x at the point x comma f of x. For example, let's say f of x were 1/2 x squared. So if we plug in x equals 1 for f of x, the y value, the corresponding y or f of x value would be 1/2. So we get the 0.1 1/2. Well, if we evaluated f prime of x at that value, we would get 1, right? F prime of x, the derivative of f of x is f prime of x equal to x. And if we evaluated that at x equals 1, we would get 1 as our output. And the interpretation is that the instantaneous slope of f of x, the original function, at x equals 1 is 1. So it's really the instantaneous slope at the point 1 comma 1/2 of the original function. And that slope is equal to 1. Another way of thinking of f prime of x, or in particular let's say f prime of 1, is the slope of the line tangent to the graph of f of x at x equal to 1 comma f of 1, which is in this case 1/2. So the line tangent to f of x at 1/2 is going to have a slope of 1, which is f prime evaluated at x equal to 1. But the next question is whether the slope of the line tangent to a function at a particular point is always equal to the derivative evaluated at the corresponding x value. And the function g of x equals absolute value of x is really a counterexample to the claim that the slope of a tangent line to a function at a particular point is always the derivative evaluated at the x value of that point. If we look at the line tangent to the function at x equals 0, so it would be really the line tangent to the function at the origin, it's the line y equals 0, which is effectively the x-axis. But the slope of that line is 0. But the derivative at that point is actually not defined. The derivative does not exist at x equal to 0. Now you might be wondering why the derivative of g of x equals absolute value of x is not defined at x equal to 0. Well, recall that g prime of x is the limit as h approaches 0 of g of x plus h minus g of x over h. But if we're interested in the derivative of g of x at a particular point a, then this limit becomes the limit. So this is g prime of a. G prime of a is the limit as x approaches a of g of x minus g of a over x minus a. And if that doesn't make sense, just realize that in this case, x has replaced x plus h, and a has replaced x. And so h in the denominator, remember this was really x plus h minus x. So if we let x replace x plus h, we have x, and a replace x, we get a, so we have x minus a in the denominator. Now when a is 0, we're looking at the limit as x approaches 0. Approaching 0 from the right, the absolute value of x behaves like y equals x, which is a line of slope 1. It has fixed slope 1, no matter how close we get to x equals 0. So the limit as x approaches 0 from the right of g of x, well, this is the absolute value of x, minus g of a, the absolute value of 0, over x minus a, so over x minus 0. Well, this is plus 1, because coming in from the right, this function behaves like y equals x, and y equals x has a fixed slope of positive 1. The limit of this difference, quotient of differences, I should say, is positive 1 coming in from the right. But coming in from the left, the absolute value of x behaves like y equals minus x, which is a line of fixed slope negative 1. So the limit as x approaches 0 from the left, the absolute value of x minus the absolute value of 0 over x minus 0 is negative 1. And remember, limits exist if the left and right limits are equal. So in this case, we're looking at this limit where, in the particular case in which a equals 0. And at a equals 0, this limit fails to exist because the left and right limits are different. But remember that the derivative of g at 0 is defined as this limit. And if the limit doesn't exist, and remember the limit does not exist in this case because the left and right limits are not equal, then the derivative does not exist at x equals 0. So you might be asking, where does the derivative exist? Well, it exists everywhere other than x equal to 0. So for all real numbers, all real values of x other than x equal to 0. And if you're wondering how I knew that, well, x equals 0 is the only point where you have a very sharp difference in slope coming in from the left and difference between the slopes coming in from the left and right. Pick any other point. Let's say we picked x equals negative 1.5. Approach negative 1.5 from the left, your slope is the same as if you're going to be approaching from the right. In fact, it's 1. It's negative 1 in both cases. And at x equals 0, there is a drastic change. This is not a gradual change. Immediately goes from being negative 1 to the left of 0 to positive 1 to the right of 0. And so this function absolute value of x is not differentiable at x equal to 0. So this video opened our eyes to the idea of differentiability. We'll be continuing our discussion of differentiability in the next video.